So to give you a quick overview of us as a company, we're really focused on preclinical, so just from early screening through IND. We're both discovery and regulated and non-regulated work. And in honor of the World Series, I thought we'd start talking about some testosterone and other steroids. And beginning with that, we've moved into the steroid pathway analytical work for a variety of customers, and I don't know why the rest of the slide didn't. Oh, that's what it did when it imported it. Okay. So we've gone and developed in vitro assays to really map out all of these pathways. And again, when you develop assays for steroid analysis, there are issues because the same enzyme will make lots of different, will work on several different substrates. And so determining whether you're really blocking that enzyme, or you're blocking just a single substrate, or you're blocking the whole activity of an enzyme. And so as we have built these in vitro assays, we've learned a lot about concentrations of analytes in assays. So if you take a compound collection, and you dilute them in DMSO, and you say, well, what's the purity? So we got high purity numbers here, basically up in the 90s for this whole big set, and the percent of expected concentration is, normalized somewhere around 80%, which is kind of what you would expect of discovery samples. You throw them in buffer, and all of a sudden everything comes down. The purity numbers actually go up a little bit, mainly because you can't detect the impurities anymore because the concentration has dropped so much. A different way of plotting that is to plot the percent of expected concentration in the DMSO, so you dilute it in DMSO, versus the concentration if you dilute it in buffer. And what you should see is things lie along this line. They don't, because they're a lot more concentrated in DMSO than when you dilute them in buffer. A different way, when you dig a little further into this kind of effect, so this is the concentration effect on concentration. And what does that really mean? If you are doing in vitro assays and you start, say your top concentration is 25 micromolar, and then you make your serial dilutions down to lower concentrations, and you plot and say, what is my concentration percent of expected? So ideally, if everything was right, we would be at 100% all the way through. We'd have a nice straight line. For some compounds like this compound, which has a solubility limit, the top one here, as you go to lower concentrations, it becomes closer to the expected concentration because you now are at the solubility. You're not limited by solubility anymore. Other compounds that have absorption effects do like the one on the bottom here, which brings it all the way down, and you lose and have a much lower than expected concentration because it's absorbing to the plastics in the process. Others have some very odd behavior, like this red one, which is kind of going up and down in the middle. When you have precipitation at the high concentration, it drags more stuff out. You reach a range where you can actually have a little bit higher concentration without the precipitation, but then it drops off because of absorption. What all of this, the purpose of all of this is that when you're used to looking at IC50 plots, you have error bars in the y-axis. That's a very common thing. What's the error in the y-axis? You don't ever see error bars in the x-axis. That's because biologists just assume that what they put in the well is, or what they intended to put in the well, is what's really in the well, is what's really being exposed. And that's not always the case. So if you're really trying to get good, reproducible IC50 numbers, then you have to understand what's happening with the solubility of your compounds. The ones that go to the extremes are not a problem because they tend to be reproducible. It's the ones that do this middle funky behavior that cloud up that become very irreproducible, and you have very high CVs with those samples. So moving on from that, when we go to in vivo measurements of steroids, and we've got different steroids we look at, but let's take testosterone. And what we've got is, what I'm plotting here are vehicle controls, no dosing with compound. And we're starting out with the diamonds are the 2-hour points, and then on this side it's the 5-hour points. And this is the initial mouse data. I'm just taking dose with vehicle, 2 hours later, take testosterone levels, and there are 6 animals in the group. So you got 6 animals put in a pen together. They've been living together for a few days, and you dose them, and then you take plasma levels. And what you notice is you got one up here that looks like he's the alpha male who's beating up on the one down here that's having trouble, and the ones in the middle are just kind of hanging out. And that's a model that sits no matter what they were dosed with, no matter what we did. And it wasn't a, if you start thinking circadian rhythm thing, we couldn't find a way to solve it that way completely. But it exists both at the 2-hour, 5-hour, the same guys still got the high levels, and other people have low levels. But eventually, working with refining the way we did the assay, the way we do the animal portion, or work with the animal facility on doing the animal portion, we were able to bring it down to where the response was pretty much flat across all 6 animals, so that we could get much tighter data, much more consistent data. And so our focus here is to deliver the assays that are needed, that the customer needs. We've added a tremendous number to improve the selectivity and look at selectivity of the compounds, improving the precision, and improving to get better correlation between the in vitro and in vivo models. And the customers that we do this with, one company in particular, we took them from the very beginnings of the very first studies all the way through to candidate selection in less than 18 months, and investors were very happy with that company, so their Series B financing was better than $15 million once they got to this point.
Thank you very much, Ken.